Welcome back. Part 1 will be foundational for this video, so make sure to go back and watch that if you haven't already. You can find links in the description for part 1 and 3 for this series. So for this problem, we're looking at finding the maximum and minimum values of this quadratic function over a closed interval. Of course, this is a Calc I review problem to kind of set up the method that we're going to use for this. So I like to start these problems by drawing the input space. That way I can get a list of all the pieces of the geometry and outline everything I need to test. In this case, our function has only one variable, so we're in a one-dimensional space. So this is f of x, so it's a one-dimensional function. So we need only one axis. We'll call it the x-axis. The constraint has two boundaries at x equals 3 and x equals 6, these two. So I'll label some tick marks at, say, 3 and 6. Draw a couple of points there. 3, 6, and the interior is a line segment between them. All right, so that's the entire input space. Next, we'll build a table to keep track of all the points we need to test. So we'll have a geometry column to describe where each point comes from. This column is not absolutely necessary, but it does help us start with a checklist, which I think is really useful. Then we'll need columns for the inputs, which in our case is just x, so we'll have an x column. Lastly, a column for the output, f of x. So this is just a table to keep track of all of the different possible candidates for maximum minimum points. Next, we'll use the geometry column to make a checklist, since we'll need to test every piece of the geometry. We can always start with the interior. Interior. There we go. In this case, the interior is one-dimensional, so moving down the list we saw before, the next pieces will be the vertices, of which we have two. The left vertex, and the right vertex. So we've got three different pieces of geometry to test. We can automatically read off the locations of those actually here. The left vertex is at x equals 3, and the right vertex is at x equals 6. So not too bad there. For the interior, on the other hand, we'll have to find critical points. So this is just regular Calc 1. We'll start by taking a derivative of f with respect to x. So actually what I'll do here is I'll rewrite the function here. F of x is x squared minus 8x plus 17. And then the derivative of that, f prime of x, is, well, 2x minus 8. We want to know where the function levels out, which is where the slope is 0. So that's a function that gets you the slope at any point. We want to know where is that equal to 0. This is a linear equation. We can solve that pretty easily. Move the 8 to the other side and then divide by 2. So we get x equals 4. Not too bad there. That's our interior critical point, so we can add that to the table. So I'll slide over here. We have x equals 4 in the interior. I like to graph the critical points also. This will show us whether they are in the region or not, because that's pretty important. So 4 in particular is just a little bit bigger than 3. Not quite up to 6, so it shows up right there. Like that, there we go. That actually is in the region. If it was not in the region, then we can throw it out immediately. In this case, we do have to test all three of those. Now, based on some theorems from Calculus 1, we know that the max and min must be at a critical point or on a boundary. And we have all of them. We have the boundaries and we have the interior critical point. So our last order of business is to evaluate the function at these points and determine which ones are the max and the min. So I'll do that on a separate sheet here. I'll just go back to this one. We already have our function there. We're going to evaluate f of 4 first. F of 4, there we go. Now if f of x is x squared minus 8x plus 17, f of 4 must be 4 squared minus 8 times 4 plus 17. So then 4 squared is 16, 8 times 4 is 32, with the minus sign of course, and then plus 17. Now 16 is half of 32, so 16 minus 32 makes negative 16. We still have that plus 17 there. And 17 minus 16 is a nice clean 1. All right, so I'll plug that into the table. We have f of 4 is 1. So f of 4 is 1. There we go. And we'll do the same thing with our other points. Our next one was 3 there at the left vertex. So we'll say f of 3. Once again, following this pattern here, 3 squared minus 8 times 3 plus 17. 3 squared this time is 9, minus 8 times 3 is 24, plus 17. I think I'd rather do the 9 plus 17 first this time. That makes, what, 26? 26 minus 24. And 26 minus 24 is a nice clean 2. Once again, we can plug that into the table. if I can see everything at once here. Not really. F of 3 is 2, so f of 3 is 2 in the table once again. There we go. Then we just have our right vertex, which is at 6, so we'll plug that in as well. F of 6 is 6 squared minus 8 times 6 plus 17. 6 squared makes 36, minus 8 times 6 is 48, plus 17. 36 and 48 are 12 apart, and the 48 is bigger, so that makes negative 12 plus 17. And 17 minus 12 is 5. We can fill that in on the table. F of 6 is 5. I'll just write that over here. F of 6 is 5. All right, and that's all we need to find our final answer. The smallest value on the table is 1. Again, we're looking for the maximum and minimum values, which just means output values. Output values. So our smallest output value was 1, and our largest output value was 5. So those are our min and max. Lastly, we can present our final answer. You can say it kind of however you want here. I like to say it in a very specific way. I'll say f of x attains a minimum value of 1 at x equals 4 in our case. So the value itself is 1, that's an output value, and the input that got that value was 4. So f of x attains a minimum value of 1 at x equals 4. And then same thing, f of x attains a maximum value of 5, was the largest one that we found, at x equals 6. All right, we can box that. That's our final answer to the problem. And that's it. In the next video, we'll apply this same strategy to a two-dimensional function, which is what we're interested in Calculus 3. All right, I'll see you guys over there.